Good evening to all of you. I am Singh Meena, University of Agriculture Sciences, Bengaluru. And now I will be presenting a cost-effective approach to improve the post-harvest feed quality in Indian mulberry. So this is the my flow of the presentation. In first part, we are discuss about the importance of the sericulture in agriculture, and second part we discuss about the approaches followed to minimize the post-harvest water loss in the mulberry, and then output and finally conclusion. So coming on to the main part of the my presentation. So first of all, I introduce to you my crop. My crop is a mulberry. Mulberry is a perennial woody plant system commercially grown for the leaf because the mulberry leaf is a sole food for a silkworm Bombyx mori, and it is well established. The silk production is dependent on to a quality of the leaves. So if you are give a good quality of the leaf foliage to the our silkworms, I means this is expected. We also get a good quality of the silk as well as the yield also improve. So now I addressing a one question: can we improve the post harvest leaf quality? So first of all, we are understood why we want to improve the post harvest leaf quality, because we know the silk industry is totally dependent on the leaf foliage of the mulberry. So after the harvesting of the mulberry leaves, the leaves are quickly close the stomata, but the cuticular pores are continuously release the amount of the water. So our quality of the leaves are decreased because the content of the water are decreased. So this type foliage, if you are provide our silkworm, so means this foliage are adversely affected the feeding behavior of the silkworm and adversely affect the quality and quantity of the. So already some researchers are developing some novel ideas for improve the post-harvest leaf quality, including our lab members already identified some genes from the Arabidopsis thaliana. These genes are directly related to the wax synthesis, and they are transferred into the mulberry and develop transgenic mulberry plants. And they are observed under the normal condition. The transgenic plants are showing the more wax deposition, and they also analyze after the harvesting of this transgenic plants leaves are showing the more water holding capacity. So we will also thinking in the same way, and we will try to can we also improve the post harvest leaf quality. But we are decide we not use any biotechnological tool, and we are not modify our mulberry plants. So we thinking about the why not we use any agronomical approaches. So these approaches are more beneficial to the our farmer as well as the farmers also adopted easily. So keeping these points in mind, we will also thinking in the same way, and we are choosing two genotypes of the mulberry. First is the Dudia white, and second is the Matikera white. So both genotypes are divided into three groups, and we impose the limited water regions. Like as the 100% it means the fully irrigated plant, 60% and 40% field capacity. And our limited water conditions are confirmed by the gravimetrical approaches. So after imposition of limited water condition, we confirm the whole plant level the confirmation of the limited water condition, and we record the several physiological parameters including the relative water content. Why we want to take the relative water content? Because the relative water content is a key factor for determining the leaf quality of the foliage, and we are observed our 60% and 40% these limited water plants are showing a significantly low relative water content compared to the 100% plants. It means our plants are addressing a limited water stress. So already researchers are give idea about the under the adverse environmental condition, plant are synthesize the some and modify themselves and protect to themselves against the adverse environmental condition. Some plant species are convert their leaf to the spines, and some plant are developing more leaf hairs, as well as some plant species are synthesizing more epicuticular bracts and control the excess water loss. So we will also think can our mulberry plant also develop a secret strategy for control the excess water. So we going for the further process and confirm the X load in the both genotypes under the different water regions. So we identified the our 60 and 40% regions plants are showing the more content of the wax comparison to the 100% plants. It means the our plant also develop some defense mechanism, but we don't know why the plant are synthesize the more wax under the limited condition, moisture condition, and why what is the main role of the wax load. So for this confirmation, we check the water loss in the both genotypes under the all three different regions, and we identify the significant difference between our control as well as the limited water plants. It means our limited plants are showing the significantly lower water loss compared to the fully irrigated plants. So we are saying that our limited plants are synthesize the more wax, or maybe that these wax are directly involved into the control the excess water loss, especially cuticular water loss. And same friends, we are going into the another genotypes. So, but this is data is not sufficient for the arguments. So now we are understood the what is the main function of the wax. So for confirmation, this one we are going for the check the correlation between the moisture retention capacity and wax load in the both genotypes, and we have found a strong correlation between the both parameter. In x-axis, we mentioned the moisture retention capacity, and y-axis the wax content. So our data is strongly suggested under the fully irrigated plants are showing the less wax content. So that's why the moisture retention capacity is the very low. But if we are look at our 60 and 40% limited water region plants, so this plant are showing the significantly more wax content compared to 100%. That's why the moisture retention capacity also more. So that this data is suggesting that if the wax content are increased, it means the moisture retention capacity also improve. So we are sure now the wax are play important role for the controlling the excess water under the limited water condition. So this is my conclusion of my presentation. So under the limited water condition, our plant are synthesized the more abscisic acid in the root zones, and this abscisic acid are transferred from root zone to the leaf and control the excess water by the closing of the stomata. In second way, the abscisic acid are triggered some wax synthesis genes like a SINE1, and these genes are produce the more waxes and control the cuticular pore and control the excess water loss. If you are control the our excess water loss by the closing of the stomata and covering of the cuticular pore, it means moisture retention capacity also improve. If the moisture retention capacity improve, means the leaf quality also improve. So this is a very basic and agronomical approaches. These are provide a better way to control the excess water loss and improve our leaf quality. And we are giving a better foliage to the our silkworm as well as maintain the requirement of the silk industry. So this is a agronomical approaches, and this is the my take message. It means the desiccation stress can increase cuticular resistance, minimize post harvest water loss, and hence can be contribute to the leaf quality. And I would like to thank the Indian Council of Agriculture Research for providing me senior research fellowship for my research work, and Department of Biotechnology India for funding the project, and Dalhousie University and my host University of Agriculture Sciences, Bangalore, for providing me opportunity for presenting my part of the research in the Global Reach 2022. And I would like to thank to my chairman, Dr. Natraja and Karaba, and my teammates for support me during my research work. Thank you one and all for your kind